Okay, so let's start. So this is our main object, interlacing particle configurations. So we'll deal with interlacing particles on z times z plus, which means that we will have one particle on the first horizontal line, two particles on the second horizontal line, three particles on the third one. All of them will have integer coordinates, and they will satisfy the following interlacing conditions that the particle here should sit between two particles here and here, which formally can be written like that. We have to agree that on one side we have strict inequality, on the other side non-strict inequality. That's not very important, but well, let's agree on it in this way. So usually we will identify particle positions with Young diagrams, saying that this row of particle is the same as Young diagram with 5 rows, and the identification is given through these formulas. So we reorder coordinates and make them strictly decreasing. That's all what's happening. So very simple formulas. Okay, so we want to start with interlacing dynamics, so which fills the formalism introduced by Alexei. So recall that everything starts with two transitional probabilities. One is this one, another is this one. So we fix some specializations. In our case, we'll have A specializations, which will be just single variable specializations, and B specializations, which will later be something more complicated. And we can formally define two matrices of transitional probabilities like that through Schur polynomials. And our first aim will be to see that these transitional probabilities turn out to very explicit and simple transitional probabilities if we evaluate everything what stays here. Okay, so first, the main object that we see depends on these specializations. So what are our specializations? So they are the following. So we have A specializations. Each of them will be just single variable, and this variable will be 1. So very simple specialization. Another specialization that we need, this B, will be specialization recalling the formulas with generating function. There were alpha parameters, beta parameters, and gamma parameters. So we have the whole the one parameter beta, which is equal to some b, and everything else is 0. So that's our specialization that we need, which means that the zeroth complete homogeneous function, which is 1, well, it always goes to 1, and the first complete homogeneous function goes to b under this specialization. All other ones goes to 0. Okay, now just putting it into this formula, that's the two kinds of transitional probabilities that we have. One is this one, another is this one. It's still not very explicit because we still don't know what stands behind these symbols, but let us understand at least what stands here. So here is the following proposition. So skew Schur polynomial evaluated at specialization B is 0 unless the following property holds. So the all coordinates difference between coordinates of lambda and mu should be between 0 and 1, which on the graphical language it means that two Young diagrams, here is this is lambda and this is mu, bigger one. They should differ by vertical strip, which is some collection of boxes which with at most one box in one row. And in this case, the value of skew Schur polynomial is just can be computed as a power of this parameter b that we have. Okay, and second proposition is that Schur polynomial evaluated at single variable 1 is again very simple. This is 0 unless two Young diagrams differ now by horizontal strip, which is a collection of boxes which at most one box in each column. And in this case, if indeed they differ by horizontal strip, then the value is 1. So how do we prove them? Well, it's very similar to what we did yesterday, because everything follows from the determinantal formula for skew Schur polynomials. Well, this formula just substitute, that we know how this thing's evaluated. Look at the matrix, see that, unless this condition satisfies, this matrix has huge blocks of zeros and its determinant is 0. Otherwise, you see that this is a product of matrix element. Okay, so what it means, this evaluation. Recall that now we will define transitional probabilities on the whole array of these interlacing particles through these formulas, through these Markov operators. So how do we do this? Well, the general definition tells us the following construction. So we will define it sequentially. So we will have discrete time Markov chain. The time will increase. It will be our parameter t. So given particle configuration at time t, we will define particle configuration at time t plus 1 sequentially. First we will define the particle at level 1. So first we will see what happens with this particle, then we will see what happens with these 2 particles, then with these 3 particles, and so on. First let's start from 1 particle. For 1 particle everything is very simple. We don't need any commuting Markov operators. We just take this transitional probability in case when n equals to 1. And evaluating what happens here, we see that transitional probability turns out to be a very simple formula. So you have 1 particle. At each moment of time, it jumps to the right with probability b to the 1 plus b and stays put with probability 1 divided 1 plus b. So this is just a simple random walk, simple Bernoulli random walk with probability of move given by this formula. Okay, now a little bit more complicated. So suppose that we understood what happened, say, at first 2 levels. We want to understand what's happening on the 3rd level. Again, the formula which was written by Alexei on the blackboard says that we should compute, so that to understand what is new, so new position, so new is a new position at level n at time t plus 1. So it depends on the position at time t plus 1 at level n minus 1 and at position at time t at level n. And it's given by the following formula. So now we just substitute. Well, we have the definition. We substitute. We notice that everything, all these complicated factors that we even did not evaluate, they cancel out. They're not important. What is left are only these factors which we just computed. So, and after substituting the formulas, we see that the answer is very simple. It is just b to the number of boxes in the new position minus the total number of boxes in the last position, which informally means the following, that each particle independently jumps to the right with this probability p, divided by 1 plus b, unless this contradicts interlacing conditions. So let's put it in more graphical representation. So what happens? So we have our configuration at time t, how to get configuration at time t plus 1. So each particle independently flips a coin. This is biased coin with probability of heads being p. So if particle see heads, then tries to jump to the right, but perhaps it contradicts interlacing conditions, and then this contradiction is resolved by the rule that the particles are heavier when they're on the bottom, which means that this particle will push particles on above it, while this particle, if it goes into this, just nothing will happen. It is blocked. So this is kind of dynamics that Alexei spoke about. And you see that now the construction, this definition with Bernoulli steps doesn't involve anything about Schur polynomials. It's just simple Markov chain. So this is the good news about it. Okay, now I will show you some simulation, and I will give some graphical image. It turns out that this dynamics, which is introduced through Schur polynomials, is very much related to other object which comes with some combinatorial probability, which is called domino tiling of Aztec diamond. And this, our particle configuration, its evolution can be identified with some tilings with dominoes. So let's take a look and see what is it. So I'll first run some simulation, which was written by Patrick Ferrari. So this is our particle configuration. So I will start some dynamics. So the particles start jumping to the right, at most by 1. So now let me stop it at some moment of time and explain what's happening here. So our particle configuration at some moment t can be identified with tiling. So you see what's happening here. You have this thing like rectangle, and you try to tile it with dominoes of size 2 by 1. So you see there is a tiling, so there are dominoes of this kind and this kind. You may wonder why here are 4 colors but not 2 colors. This is simply because of the following fact, that we can also draw like a checkboard here. So draw everything, all the lattice into 2 colors, and then you can introduce 4 colors. And then you can introduce 4 types of dominoes instead of ones. But anyway, what you see here, that if you take one type of dominoes and put just particles on it, and take also another type of dominoes and also put particles on it, then you end up with just this interlacing point configuration that we were speaking about. And more interestingly, if you consider just uniform measure on all domino tilings, so you just consider this rectangle, tile it uniformly, and then project on the particles, then you exactly get configuration of our Markov chain at some moment. So that's what we see. Interestingly enough, looking at this picture, you can see lots of features of it, like near the corner, as though there is uniformly random configuration, but somehow near the corner it looks absolutely not, something special is happening. You see that the configuration is very special. We will come to that later. Okay, so that was our first example. Second example is what happens if we do limit to the continuous time. It will be much more similar to what exactly Alexei was speaking. So our dynamics for now was discrete time dynamics, that at each time something was happening. Now we can do a usual limit. Well, usually sum of Bernoulli random variables converges to a Poisson process in a certain scaling limit. And the same we can do here, which means that we send the parameter of our Bernoulli random variable to 0, at the same time we scale time, and then our discrete time dynamics turns into continuous time dynamics. So what does it mean? Actually, it means that now, well, what we had before is that at each moment of time, lots of particles can jump. Now, since we are in continuous time, at each moment of time, only one particle will be able to jump. And formally, what we will have is that each particle will have an exponential clock of rate 1. All clocks will be independent, and when clock rings, particle will attempt to jump to the right. Let me again tell you how the interlacing conditions will be preserved. So let's see with pictures. So if this particle tries to jump to the right, but if the more heavy particle is blocking it, then just it is blocked, so nothing happened. On the contrary, if this particle tries to jump to the right, then it is blocked by lighter particles, and then it is not blocked, it just pushes this particle and moves them to the right. Okay. So this particle dynamics can again be identified with something interesting. Now it's some surface growth model. So let me show you another simulation of how all these things evolve. It's again written by Patrick Ferrari, not this one. So first, that is our particle configuration that we start from. So let's start the dynamics, see how it evolves. You see that particle starts to jump. We can give more time. So something is happening. Turns out that picture will be much more interesting if we do some graphical representation of it. So instead of particle, let's look at the following thing. So basically, this is still particle configuration. So these, so you see there are red points. So red points are still our particles. However, you can complement these red points to the whole big picture, which will be like a tiling with rhombi of 3 types. Okay, so this picture is identified with our particle configuration. And then when you start move, then you see that you can view, well, if you think about it as about 3-dimensional picture. So this is some kind of stepped surface. I hope that you can see it. And then the evolution, this particle configuration evolution, is the same as some growth model of this surface. So it's evolving in time. So in this way, this formalism of Schur dynamics brings us some growth process. Okay, let's stop it. Okay, now the step that we did now was that we passed from the discrete time to continuous time dynamics. Well, one can also wonder what happens if we want to speak not only about continuous time, but also about continuous space. So what is continuous time, continuous space analog of simple Bernoulli random walk? Well, usually this is just Brownian motion. So we want to study some Brownian motion related object, which again will live on the interlacing particle configurations. So how to construct such object? So this construction was introduced by John Warren 7 years ago. So first, the state space now will be a set of interlacing particle configurations, but in continuous settings. So now all the particles have not integer, but real values. So like here. So we will define our process inductively. So there will be some Markov dynamics on these interlacing particle configurations. So first let's take a look at the bottommost particle. It will evolve just as standard Brownian motion, so something like that. This is the evolution of this particle. Now suppose that we have defined, say, this particle, and we want to understand what's happening with this particle. Then the definition is the following, that given trajectory of the first particle, like this one drawn in red, the trajectories of next two particles on the second row are just independent Brownian motions which are reflected by this trajectory. Well, you may ask, what does it mean reflected? Well, there is a certain probabilistic construction making sense of reflection. Just simple example which is good to have in your mind is that if you try to reflect Brownian motion by the just horizontal line, then you just get absolute value of Brownian motion. So it's like the things that you expect to see when you reflect. And so it makes sense in general. And more generally, you can define your process inductively. So if you want to understand what's happening, say, with this particle, then you should do it already know the trajectories of this particle and this particle. And then trajectory of this particle will be again U independent Brownian motion reflected by this trajectory and this trajectory. So why is it interesting to study such a strange object, some reflected Brownian motions? Well, it turns out that if you start from zero initial condition, that means that at time 0 all particles are at position 0, then this process has lots of connection with random matrices. For example, if you restrict your dynamic to the nth row, which means you look, say, at these 3 particles, or maybe at these 2 particles, and this will be exactly Dyson-Brownian motion, which is the process of eigenvalues of random Hermitian matrix that happens when the entries of this random Hermitian matrix evolve as independent Brownian motions. Also, if you fix any time and look at the whole configuration, so you look at the distribution of this whole configuration, but at a fixed moment of time, and this can be also identified with some random matrix distribution, which is so-called GUE minor distribution. So this particle configuration is identified with eigenvalues of Hermitian GUE matrix, its top left minor, then smaller top left minor, and so on. So there are exactly big matrix and n-1 minor. So the big matrix has n values, the smaller submatrix have n-1 eigenvalue, then n-2, and so on. And the full set of these eigenvalues exactly form an interlacing array, and its distribution will be just the same as distribution at fixed time of our dynamics. Finally, the third thing why it is interesting to study these dynamics is the fact that this is a kind of universal scaling limit for the dynamics with block and push interactions in discrete time settings. So for example, that dynamic that we started from with Bernoulli steps, in the long time limit, it converges to this interlacing Brownian motion. And also another dynamic that was in continuous time with particle jumping at exponential times, again converges to these dynamics of these interlacing Brownian motions. So you can think about it in the same way as like central limit theorem and its generalizations tell us that the uniform scaling limit of random walks is Brownian motion. In the same way here, the universal scaling limit of these processes on interlacing particle configurations with block and push interactions is again the system of interlacing Brownian motions. Okay, so this was our first example of various processes of interlacing particle configurations. Another example came, well, it's a little bit was shown a little bit already, but let's go to it into more details. So another example comes from lozenge tilings. So what are the lozenge tilings? We will be interested in tilings by rhombi with angles pi/3 and 2 pi/3 and side lengths 1, which we will call lozenges. So there are three types of these lozenges, as shown here. So each lozenge is just a union of two triangles with equal sides. So there are three ways to glue two triangles. So there are three types of lozenges. So we want to tile planar domains with these lozenges. So the simplest tileable domain is a hexagon with side lengths A, B, C, A, B, C. So we can tile it like shown here and get something. Now, these lozenge tilings can be identified with plane partitions or with 3D Young diagrams. So how to do it? So start with a plane partition, which is a table filled with numbers which are weakly decreasing along the rows and columns. Then imagine that you put k unit cubes on a cell with number k. You get some three-dimensional body. Now look at this body shown here. And notice that its projection is exactly tiling. And indeed, this gives a bijection between tilings, plane partitions, and this 3D Young diagram, these three-dimensional objects. And also, sometimes it's a very good thing to think about not 3D Young diagram, but about its border, its boundary. So its boundary will be some kind of stepped surface. Then our model is just some model, simplest model of stepped surfaces in three-dimensional space. Okay, we want to introduce some probability here and to see some interlacing particles as well. So we'll be interested in random tilings. So we'll fix our hexagon and then consider some probability measure on all tilings of this hexagon. The simplest measure is, of course, uniform measure, but there are some more complicated measures, like you can say that probability is weighted with weight q to the volume, or maybe something more complicated. So let's stick to the uniform measure for a moment. So first question is, how is it related to what we speak about before? Thinking that if you look at the tiling of your hexagon, then choose one type of lozenges, say this one, which we'll call horizontal lozenges. Then put a particles on these lozenges and look at the whole picture, and you immediately realize that this is the same as interlacing particle configuration that we spoke about before. So we exactly have one particle on the first horizontal line, two particles on the second one, three particles on the third one, and so on. So these lozenge tilings are exactly the same as particle configurations. Now, now suppose that we want to study this model. We want to understand how typical random tiling for a hexagon of big size looks like. At first moment, at least, we want to see it. So to see how it looks like, to do some maybe sampling. So to do it, it turns out that the similar ideas with these commuting Markov operators helps us in this problem. So from these ideas, again, we can extract some sampling algorithm and some dynamics, which will give us our tilings. So recall that for this formalism, we first need some transitional probabilities, so some Markov operators that will compute. So how to find it? Where are Markov operators in these lozenge tilings? Turns out that very good point of view is to associate some family of non-intersecting paths to our lozenge tilings. So start from lozenge tiling. Now draw paths on the lozenges of two types. So you forget about lozenges of this type that were related to particles. You look at other lozenges and draw lines on them, like shown here. Then you see that this is just a collection of non-intersecting paths. And then tilings are in bijection with families of non-intersecting paths with fixed starting and ending point. Well, on this picture, it was a little bit not on the lattice. So we will do a simple affine transform and view picture like that, just to make it a little bit more convenient. And look at our paths. So we have some uniform distribution of all non-intersecting paths going from this collection of points to this collection of points. Now I claim that this can be viewed as a Markov chain. How to do it? Just consider some vertical section of this picture at some fixed moment in time. well, this section will be just some collection of points. So in this picture, that will be a collection of 3 points. Then if you change your vertical line, then you will get some evolution. And the uniform measure on non-intersecting paths exactly lead to Markov evolution. So that will be just Markov chain, in our case, on 3-point configurations. And informally speaking, you can say that this is a chain just given by conditioning n, where n is this side, independent Bernoulli random walks to finish at prescribed points and to have no intersections. Okay, so this is first Markov chain. Due to general scheme that Alexei spoke about, we also need some additional chains, which will be like links. So we want links to be something which changes this parameter, like which is this height c or one length of one side of the hexagon. Well, you can ask, where can we find the second chain? And this is indeed non-trivial. So I won't give you exact definition of this second Markov chain. However, it is hidden somehow in the structure of the model. So there is some symmetry between parameter t shown here and parameter s, which is side length of the hexagon. There is some symmetry between these two parameters, which gives a way to define another family of Markov chains. And then we again do the same construction as before. But when we have commuting Markov operators, then you can introduce a dynamics on the whole, not on the one configuration, not on the one family of points, but on the like 2 families of points and 3 families of points and so on, which was taught about as Alexei told. So, well, graphically it can be viewed as the following picture. So, given distribution at these points, say to define the distribution at this point, we define it just as a distribution of middle point of sequential applications of 2 Markov chains, of 2 Markov operators. So we define distribution at this point, and we define distribution at this point, and so on. Okay, so again, you can compute everything here in the same way as we computed as our first example with Bernoulli random variables, and you get to some simulation. So let me show you how it looks like, so what's happening actually. So here is the picture. So first thing to notice is that when you have a hexagon of size a times b times 0, then there is precisely one lozenge tiling. So there is only one. Since that's actually not a hexagon, it's just big parallelogram. So there is only one lozenge tiling of it. So there is no problem in, say, sampling from uniform distribution. Then you can apply these Markov chains, which come from this formalism of computing Markov operators, and you get something. Let me show you what's happening. So the size of hexagon will change. So length of one side will decrease, length of another one will increase, and something will be happening. So at each moment of time, what you will see will be just a sample from the uniform measure on all tilings. However, this gives us some sequential way to build it, which results in a good sampling algorithm. So now let's do some steps. Okay, so here we arrived at some hexagon, which is something like 50 times 50 times 50 hexagons. So now you can take a look how uniformly random lozenge tiling of this hexagon looks like. So this picture has some very interesting features. For example, you can see that here, near the boundary, something strange is happening again. So near the corner of your hexagon, you see only one type of lozenges. And this can be analyzed rigorously, as I'll show you in a moment. You also can do the same simulations for more complicated measures. For example, you can start with measure q to the volume. Let's do it. So here we will find a sample of the lozenge tilings of hexagon of size 100 times 100 times 100, and our parameter q will be 0.95. So let us see what's happening. Maybe it's a little bit, let's show it in a different way. Okay, so I hope you can see the picture. So this is our lozenge tiling, and weight of So we associate Losenstein box plane partition on 3D Young diagram and associate weight q to the volume, q to the number of boxes in this diagram. And this is a sample from this measure. So you can see that again something interesting is happening. So there are again some kind of limit shape. So the whole picture looks non-random. And there are again some frozen regions here. Okay. So let's go on and and again I want to stress that all this complicated picture arises from quite simple Markov chain, which comes from all this formalism. So that's a good thing about it. So let's discuss some limit properties of this model so that you can see that indeed it can be proved that in the limit this model is very interesting and have lots of interesting feature. Okay, so first thing that we have seen already is the statement that near the boundary something is happening. So this is usually called frozen regions. So the following theorem holds, in fact. So suppose that you take some hexagon and you start enlarging it, keeping its proportions the same, and you look at uniformly random Losenstein of this hexagon, then everywhere outside inscribed ellipse of this hexagon, the picture will be frozen, that there will be lozenges of only one type in the limit. Like, well, we can actually see it on this picture already, so that here everything is frozen. So this is proven in 1998 by Kohn, Larson, and Propp. There's an interesting generalization due to Kenyon and Akunkov, which was proved in 2005, that if you consider now Losensteins of much more general domains, so you can start with any domain with polygonal boundaries, then the same phenomenon will be still there, so that you will, in the limit, you will see some frozen region. So outside some curve, you will see only one type of lozenges. Actually, you can see that it starts forming already on this sample. It's near this corner, something strange. And interestingly enough, there is a connection with some algebraic geometry that the boundary of this frozen region is exactly inscribed algebraic curve of minimal degree. So for example, in the hexagon, the minimum degree you can get for the curve to be ascribed is the second degree. So there will be ellipse ascribed in this hexagon. So in more complicated domain, you need a higher degree, but still you find that it's like curve of minimal degree which touches all the boundaries. You can also start studying more complicated measures here. Say for the hexagon, if you get some more complicated measure like q to the volume, q to the minus volume, some mixtures of them, then you can show that still there is a similar phenomenon, that there are some frozen regions and you can still compute the boundaries of these frozen regions. For example, in our joint paper with Alexei and Eric Rains, we computed from some family of measures on the box plane partitions on these tilings of the hexagon, which brings similar pictures but with different kind of asymptotic behavior. Well, in general, problem about what happens in general domains with general measures, it remains open. So it's interesting to see what can be done there. Okay, now another result is that if you now view this picture not just as a tiling but as a three-dimensional surface, as a 3D Young diagram which has a boundary which is a surface, and look at this surface as a surface, as something in three-dimensional space, and you enlarge your hexagon, you rescale all the picture to get some random surface which has a smaller and smaller mesh, so it has smaller and smaller steps. You show that in the limit, this random surface will converge to a non-random object, which is like limit shape of this surface, which is again proved by Kohn, Larson, and Propp, and then generalized by Kohn, Kenyon, and Propp for general domains. Now you can ask about fluctuations of this surface, and this question is very similar to the asymptotic questions that Alexei introduced and studied on the previous lecture, which was on Wednesday, where he studied asymptotics of Schur measures, and through the contour-integral representations he found some asymptotic behavior of it. So here it's much more complicated to get some contour integrals. So there are some other methods how you can find asymptotics without any contour integrals, but some results are still available. So for example, if you look at the Losenstein, we know that on top there is a frozen boundary. You can ask what happens on the boundary of the frozen boundary. Yeah, on the boundary of the frozen region. And the answer will be the following, that if you do scaling, so if n is something like linear size of the side of your hexagon, if you do scaling of order n to the 1/3 in normal direction and n to the 2/3 in tangent direction to the frozen boundary, then you see something non-trivial in the limit. So the fluctuation themselves, so this like height, is governed by Tracy-Widom distribution. So this is the same distribution that arose in Alexei's lecture. So this comes from random matrices from largest eigenvalues. And the whole 2D picture locally is governed by something called extended Airy kernel. So Alexei showed something like just Airy kernel, which through these integrals and on contours which were like that. So there's extension to two-dimensional picture which is called extended Airy kernel. Then you can ask what happens with the whole picture. Like we have some limit shape. This is like maybe law of large numbers. And usually after people study law of large numbers, they want to study something like central limit theorem. So this is available here as well. And actually this result is very recent, so it was made by Leonid Petrov just maybe 1 month ago. So the result is the following. So after you subtract the expectation, which is what law of large number predicts, in the limit you get some object which is known as Gaussian free field. Actually it was already discussed during this school, but mostly in the discrete settings when we spoke about discrete Gaussian free field. This is a continuous analog of this thing, or you can view it as the limit of this discrete Gaussian free field, so this continuous Gaussian free field. It's a little bit more complicated object because it's not just a function, it's more like a random distribution, but it's well known to physicists. They say that it is something like the simplest possible object, but from a mathematical point of view it's not so simple. And you can prove that fluctuations indeed converge to this Gaussian free field here. Finally, you can also study what happens in this picture in some local regime. So you look at some small part of your hexagon, so the hexagon is huge, but you still sit locally near some point and see what's happening in the neighborhood. So in the neighborhood, like boundaries disappear, and you see that some lozenge tiling of the plane. So we ask, is it true that your probability measures on these lozenge tilings converge to something meaningful? And indeed it can be proved. So now there are various approaches to that, and it can be done in various generalities. So that indeed locally near every point in your hexagon, you have convergence of your uniform measure on tilings. So some more complicated measure like Q to the volume on tilings. These measures converge to some translation invariant measure on the whole plane, and this measure can be characterized. In fact, this measure is very similar to what Alexei obtained as a sine kernel. So this is some extension of sine kernel. So sine kernel, this is some like measure on point configuration in 1D lattice, and this is some measure on 2D lattice. So this is extended sine kernel, while its projection on 1D lattice will be still just usual sine kernel. So that's the reason for telling this is extended. Okay, so these are some kind of theorems that you can obtain here. We show that indeed there is some very much non-trivial limit behavior. Now let's come to yet another model, which again Alexei briefly mentioned. So these are free three-dimensional Young diagrams. Recall that first we were speaking about box plane partitions. So our plane partition was sitting in a box, which made it possible for us to speak about uniform probability measure, because there were just finitely many 3D Young diagrams, so we could speak about uniform probability. Now we want to remove this condition on fixing box. We want to speak about any arbitrary random 3D Young diagrams. So we'll speak about plane partitions that Alexei also showed. So we'll be interested in skew plane partitions. What does it mean, skew plane partition? So you take some shape, which is just set theoretic difference of the quadrant minus some Young diagram, like is shown here. Then you fill it with integers in such a way that these numbers are weakly decreasing along the rows and columns. So something like is shown here. The only condition you want is that somewhere far, all numbers become zeros. And again, this this array of numbers can be related to some three-dimensional object. Again, so we put 10 cubes here, 9 cubes here, 7 cubes here, 8 cubes here, 6 cubes here. So you get some huge object, and you want to study some probabilistic properties of it. So what Alexei already told, but I want to mention it again, that this thing can be identified with a sequence of Young diagrams. So how do we do it? Well, we just look at the vertical sections of this picture, you see that this point of view of vertical section is very good. It was good for the box plane partitions. It is good here again. So here you have one Young diagram with one row 3. And you have some Young diagram with row length 6 and 1. You have Young diagram with row length 5 and 5. Then row length 8 and 4. Then row length 10, 5 and 3. Then 7, 3. Then 9, 6, 1. Then 8, 4. Then 6, 0. And you see that these Young diagrams, on some moments they grow, on other moments they decay. So there is like steps, up, down, up, down. So how to understand when you step up, when you step down? To do that, just look at the boundary and see that when your boundary goes up, then Young diagram grows as well. So for example, from 3 to 6 boundary goes up, so this Young diagram is smaller than this one. But when your boundary goes down, then your Young diagram decreases. So here boundary goes down, and you see that from this Young diagram to this, your Young diagram decreases. So you get this sequence. Now, as I told you already, there is no uniform measure because there are infinitely many such objects. But you can still introduce measure q to the volume. It turns out that if you sum q to the volume over all skew 3D Young diagram, then it will be convergent. This gives you a way to introduce indeed probability measure on all these objects. And the proposition that Alexei hinted the proof that q-plane partitions with measure q to the volume, they give rise to the Schur process. And this has two very important corollaries. First is that since it's a Schur process, and there are some integral representations that Alexei showed you for Schur measures, but there are similar things for Schur processes, so we have methods to do some asymptotics analysis of this model. This is the first thing. And second thing is that since it's a Schur process, we can again use these Markov chains which map Schur measures to Schur measures, Schur processes to Schur processes, to do some sampling. So I won't give you exact algorithm how to do the sampling. This follows basically from the formulas that we've seen already. But I'll just show you some pictures so you can play with with boundary with your skew Young diagrams and get very different classes of pictures. So you should think about it as some three-dimensional object. So there is one wall, another wall, third wall, and then there is some like pile of unit cubes sitting here, or some huge 3D Young diagram. Okay, so you can see very different limit behavior in this model because you can play with this wall, and because of that get very different limit regimes. So this model with different boundary conditions was analyzed in papers by Surf-Canyon, Okonkofer-Shetikhin, Boutier, Korchan, Shetikhin, and Tingley. So there are various transitions, so you can, like in the hexagon, I already told you about convergence to sine kernel, to this translation invariant Gibbs measure, so those convergence to airy kernel, which is related to random matrices, GUE, and distribution of largest eigenvalue of GUE. Here you can find some other kernels. For example, you can analyze what's happening near the cusp. So here you see how the picture looks like. So it goes something like here and then goes back. There is something like a cusp. You can analyze what happened here. You get some other asymptotic behavior. There is a whole domain studying different kinds, what kind of kernels you can get at the limits, where else they arise. Everything is related to random matrices, so most of the limit behavior here you can obtain from this picture. You can as well obtain from some well-suited models of random matrices. Okay, so just to summarize what we saw. First we saw that when you start from these processes related to Schur measures, Schur polynomials, and these computed Markov operators, you can write down transitional probabilities which turn out to be not very complicated. They lead to simple Markov chains with just particles jump, they push, block, so nothing too complicated. However, these seemingly trivial Markov chains lead to very non-trivial behavior after you spend a long time looking at it. So simple rules give rise to complicated probability models, and that's good. This is the first that we saw. The second thing that we saw is that for these measures, they will be started from the very rich algebraic structure of these Schur polynomials, of the determinantal point process, and so on. So for these measures, we still have this structure, so we still can analyze it, like Alexei showed it, for example. Finally, it wasn't mentioned at all during these lectures. However, it is true that you can analyze the behavior of your model just looking at your dynamics. Like you can understand that, okay, locally your surface grows like that and like this, and then in the limit it should converge to something, to get some argument similar to usual law of large numbers. Okay, I think I will stop here. Thank you.